I wanted to welcome everybody to today's program. My name is John Haber. I'm the Field Services Director for the California Preservation Foundation. Today's program is part of a five-part series called Home Safe Home, and today's program is entitled Retrofit Projects. It's going to be a deep dive into retrofits. There's going to be a lot of information covered, so we encourage you, if you do have questions, to ask those questions as early as you can. You can use the Q&A box for that, and I will be monitoring the Q&A box. There's also an option for you to upvote questions that you see in the Q&A box that you think should be answered by our panelists. We have a large panel today. There's going to be a lot of presentations, and we'll try to move through it as quickly as possible. And to start off, I'm going to introduce our first panelist here, John Lisak with Page & Turnbull. He's going to kick off the session and also acknowledge our partners in the program.
John, just checking, can you hear and see me?
Yes, absolutely.
Great. Okay. Welcome, everyone. My name is John Lisak, and I'm a principal and historic architect with Page & Turnbull. And we're fortunate to have presenting today structural engineers Mel Green of Melvin Green and Associates and David Koch of Structural Focus. I personally think if there were a Hall of Fame for structural engineers, these two would be in it. And I also have future Hall of Famers with me, structural engineer Maria Muhammad, also a Structural Focus, as well as my colleague Sarah Brummett, who is an architectural designer and architectural historian with Page & Turnbull. Sarah's going to help us with the question and answer sessions. So between the five of us, we have roughly a century and a half of experience retrofitting and repairing historic buildings. So Retrofit Projects is the fourth in a series of 6 workshops focused on seismic safety and rehabilitating historic homes. The first 2 workshops provided a basic understanding of how to identify historic properties and guidance for appropriate repair and maintenance. They provided background for the more technical sessions, which started with workshop 3, which was seismic retrofit basics. David's going to give an recap of that shortly. And they continue today with looking more closely at how you retrofit your home. The workshops will continue through the end of the year with increasing amounts of how-to information. So we hope you'll tune in to our remaining workshops as well. Projects involving historic homes typically require collaboration and multidisciplinary efforts. And this session is definitely a multidisciplinary effort. And it's got contributions from architectural historians, historic preservation architects, building materials conservators, as well as structural engineers. The program is sponsored by the California Office of Historic Preservation, as well as our partners at Structural Focus, Melvin Green and Associates, and the California Preservation Foundation, who is so graciously running this webinar. And the project as a whole was funded with grants from the Federal Emergency Management Association. So we've got a long list of objectives today, but what we really want to do is learn from some examples of residential retrofit projects. Look at how different housing types, construction methodologies, and parts of a house may require different seismic strategies. We're going to look at some ways to maximize the benefit of individual projects. These are really, we're just going to really touch on these, and in some of the upcoming workshops we'll go into more detail. We're also going to look at resources that we can go to think about how much it may cost to do the retrofit. We're going to look at some typical retrofit measures for historic homes and parts of your home that likely require retrofit. We're going to apply some of these methods for in keeping in mind historic features that are present in the houses. And we're also going to very briefly talk about financial incentive programs that exist. So today's agenda is a brief recap of workshop 3, in case you missed it. How you would go about evaluating your house from a structural perspective, some retrofit strategies, retrofit techniques and examples, priorities and how you may phase a project over time, and then we'll have a question and answer session at the end. But we're also going to start with a question and answer session. So we've got 3 questions just so that the panelists can get a feel for who's in the audience, and we may strategically tailor this as we go. So first question is, what region of California do you live in? The next is, did you attend workshop 3 or any of the prior workshops we've had in the series? And then, in what capacity are you interested in this topic? And that really means, are you a homeowner, an architect, an engineer, or some other things? So if you look at the poll that's up on your screen, remember to slide down, because it's necessary in order to answer all the questions.
Okay, I'll leave the poll up for a few seconds here. It seems like people are still answering. Okay, results are out.
Great. So it looks like the majority of folks in the audience are from the San Francisco Bay Area and Los Angeles. This time we have a pretty nice set of folks that are outside the state, and that's good to know. And then we have some folks from Sierra Nevada and Lake Tahoe. A good 80% of folks attended workshop 3 or one of our prior workshops. And the majority of people in the audience are homeowners, followed by architects. We've got some planners, some engineers, one contractor, and then a couple who didn't fit into the box. So thank you. That helps us understand our audience. And with that, I will hand it over to David Koch, who will recap our last workshop. David, you're on mute.
Had a moment of panic there. I couldn't figure out how to turn my video on. I'm David Koch. I've been practicing not quite as long as Mel Green has. I've been practicing structural engineering for 41 years and worked on a lot of historic buildings. So I'm going to be, I hope you can see that, I'm going to be doing the first item on the agenda, which is a recap of workshop number 3. So real quickly,
we don't yet see the screen, David.
Yeah.
Done. Try again.
Great. Now we see it.
There we go.
Okay. So in workshop number 3 a few weeks ago, we talked about seismic vulnerability in California and the fact that there are not many regions in the state that are not vulnerable. We talked about how to identify commonly found construction types for single family houses. We then talked about the California Historic Building Code provisions and the fact that that code allows us some flexibility in the retrofitting of the historic buildings, including a voluntary provision, as well as the provision to allow for partial upgrades. You don't have to do everything all at once, which leads to potential phasing of a retrofit. So seismic vulnerability, I'm not going to show all those maps that I showed last time. You get one big colorful map of the state, but you can see that all over the state, there are faults that are running from top to bottom. There's not many areas of California that are not vulnerable, and we really all need to pay some attention to this. Virtually all of California is at risk. I'm going to run through the building types that we talked about last time. Probably the most common is wood frame platform framing. We call it platform because they start, when they constructed these buildings a long time ago, they start at the foundation and then they build a first floor platform, whether that's on a slab or on a raised foundation. And then they build the wall studs up and frame the second floor. All the studs stop. As you can see, that note says studs start and stop at each floor. They build that platform, and then the workers get up on top of that second floor platform. They erect the stud walls, and then they go up and they erect the roof. So that's why it's called platform framing. A second type, which is an older style of construction than the platform framing, is what is called balloon framing. And what that means is that all the wall studs are continuous from the foundation to the roof. One of them is highlighted there. What happens when they do that is then the second floor, the ends of the floor joists are attached directly to the wall studs at the right height in one direction, and in the other direction, they just put a ledger along the face, the inside face of that wall stud, and that's how they attach the framing of the second floor. And then they go up to the roof and they build the roof on the top of those tall studs. That's called balloon framing. The third type is, again, still wood frame and probably not as common, but it's called post and beam. And that's when you have a series of vertical posts and horizontal or sloped beams that are that bear on those posts. Now, this is not locked into only wood frame. It could also be a steel frame. Some of the structures that were designed in the 50s, especially in Southern California, might be steel frame. Again, these are not as common as the platform framing or the balloon framing, but they are out there. Another type, which is significantly older and now less rare, it's not even allowed by code anymore, is called single wall construction. There's really no skeletal framing in the building. It's the vertical loads are supported by the vertical boards, generally around the perimeter of the structure, but some of the interior walls also can be single wall framing. And so you can, just thinking about it, you can understand that these vertical, usually 1x, 1x12s or 1x10s or 1x8s, they're not going to be as strong and forgiving as a wall stud system that we looked at in platform framing and in balloon framing. And often there's no foundation when they built these. These were very generally rural applications, and they didn't build foundations. They just kind of smoothed out the ground, set the wood directly into the soil, and went up from there. There are also bearing wall buildings out there. They can be brick, they can be adobe, they can be what people will call cinder block or CMU, concrete masonry units, stone, hollow clay tile. They can be a variety of these elements, but the difference is there's no wall studs behind those walls. There are all the vertical load and even the lateral load, the seismic load, is resisted by these masonry bearing walls. So if the wall were to fail, then you would lose the vertical support of the floors above and the roof above. And then I want to talk about 3 different foundations. We talked about this last time. There's really 3 different systems other than what I talked about with the single wall construction. One of them is a slab on grade. They smooth out the soil and they'll cast a concrete slab anywhere from 3, 4, 5 inches thick. The older homes may not have any reinforcing steel in the slab, but it's resting directly on the soil. There's no raised floor. There's no crawl space underneath that first floor. The second type of foundation I want to mention is what we call stem walls. And that's where you have the footing, which is the lower piece that's bearing in the soil. Then you have a short wall, which may be brick, it may be stone, it may be concrete masonry units. And that may be a couple of feet tall. Again, there's a raised floor, and that creates the void underneath the floor, surrounded by these stem walls, and that forms a crawl space. And then finally, we have what we call a cripple wall condition. Instead of having, you have the footing again, but instead of having a masonry or a concrete or a CMU stem wall, you'll just have these short stud walls underneath that are building up from the footing and supporting that first floor. Again, a raised floor with a crawl space underneath, and then a cripple wall framing underneath. These could be anywhere from 1 foot to 4 feet tall. So those are the building types that I just wanted to try to jog your memory about and how we will deal with them. I want to talk real quickly about the California Historical Building Code. First of all, there's no trigger in the Historical Building Code. So there's nothing in the Historical Building Code that says if you have a structure that has deficiencies that you actually have to go retrofit it. There's no government regulations that say they have to be retrofitted. It's only mandatory when it's triggered by other code issues. And even then, it still is the applicable code. So if for some reason the building department said you have to fix your building and it's a designated or an eligible historic building, that would require you to bring it up to the provisions in the Historical Building Code. And the last thing I want to mention about the Historical Building Code, again, is it's voluntary. It is, nobody's going to make you do it. And in fact, it allows specifically for partial upgrades. So if you have a list of 5 5 deficiencies that you need to fix in your building, it's allowed to go back and to go and do one at a time. And you could do one of these elements, go on, retrofit it, fix it, and then you could wait a few years later and do the next one if you wanted to. You could stretch these out and do them in phases, which we will talk about. I do want to mention that the California Existing Building Code does have some provisions in there for non-historical buildings, which are basically the same, except it gives you some force levels that you would these fixes would be designed for. And lastly, I just wanted to talk very briefly about why you're doing this. What are you getting if you were to choose to do a retrofit of your building? Well, the obvious is that you're getting a safer house. It's going to be safe. Has a much better chance of standing up. And it also will lower the repair costs after an earthquake. So, for example, if you were to do a retrofit of a Cripple Wall foundation, might cost you $3,000, $4,000, $5,000. That's good money spent, because in an earthquake, it could be $50,000 to fix it. So if my advice to you as a homeowner, if you are a homeowner, is really do try to prioritize the items that you want to do in your retrofit, because you want to get the most bang for your buck. So when you're talking to the engineer or the architect or the contractor, ask them if they can help you put together the priorities, and then talk about what the damages would be for those deficiencies if you didn't retrofit them, and what are the costs going to be to do the retrofit. People also ask about earthquake insurance. Well, the most important thing of earthquake insurance is probably considered the deductible amount, because it can be a fairly large number. And so if you were to get an evaluation of your house and they told you how much the repair costs that you might expect, you need to compare those repair costs to the deductible amount and see if it makes sense. But remember that retrofitting is kind of a form of self-insurance. Like I said before, if you spend the money to do the retrofit instead of spending the premium, paying the premium to the insurance company, it might make sense to go on and do the retrofit. And there are some available programs. We're going to touch on that a little bit later, but one of them is the California Earthquake Authority, which provides lower cost insurance to homeowners. And there are actually some grants out there that you can get to help you with financing. So with that, I am going to move to the next speaker. And we're going to do a little quiz next. So I'm going to sign off. Somehow. There you go. So Jonathan, are you taking over or am I reading these? Or
I'm taking over.
Maria's.
Thank you, David.
You're welcome.
Hi, everyone. My name is Maria Mohammed. I'm a practicing structural engineer, and I work with David at Structural Focus. I have a few quiz questions that I will briefly go through in the next few slides. And the intention for these questions are more or less to help you understand what is coming in the following sections of the workshop, and also gauge how much of the prior workshops information has been helpful for you to understand what retrofits are required. Can everybody see my screen?
I can see it, Maria. It's John.
Okay.
Yes.
Thank you. So the first question on the quiz is looking at this photo of an earthquake damage. What kind of retrofit you think is required to address this type of vulnerability? Let us know.
And Maria, sorry, the quiz is covering up that portion of the screen. If you could drag it out of the way.
Yes.
We had a lot of quick answers, it looks like, so I think I can end the poll now.
Okay. I'm going to give you the answers after the technical part of the presentation. And looking at this photo, what retrofit you think solves this problem? I hope we also have a quick answer for this one.
Yes, it was pretty quick. 14 people have already answered, so we can move to the next if you'd like.
This one even has helpful arrows.
Okay. 16 answers on that one.
Okay. Last but not least.
Okay, we have 17 answers on that one, so I think that one's done too.
Okay. Thanks, John. We will go over the answers for these quizzes in a few minutes after we go through retrofit strategies and retrofit techniques and examples, and then we'll bring up the same photos again and then discuss them in detail as to how the retrofit could have prevented that type of failure. And I'll pass it on to Mel.
All right, thank you. Trying to figure if you see my screen or not. Let's see, it is a slideshow.
Not yet.
Oh yeah? Boy, I had this perfect a minute ago. Now? Can you see me now?
We can.
We do, yeah.
Okay. Yeah, let's see what we can do here. All right.
We don't see the like the slideshow version
Yeah.
yet. Okay.
Hang on. Okay, sorry for the delay there. Want to talk about, okay, want to talk about looking at your house or various buildings and see what we see. And first I want to mention that buildings, for the most part that we're dealing with, are what we call box type structures. And if you think about a box, how relatively rigid it is, whether it be a simple shoebox or a grocery box, you can envision the walls and the sides of the box as being shear walls, the top of the box as being, well, our floor or roof, but we call it a diaphragm here. And what we're trying to do is make our box adequate in strength and its configuration. We're also going to look at load path. How do the loads get through our building to get to the ground from the roof? And then connections of how we connect everything together. I used to say that the three most important things in real estate were location, location, location. I think in structural engineering, it might be connections, 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 because that's often where buildings fail. Let's take a look at box type structures again. And this house, for example, let's look at its layout and configuration. What you see on the right is what I'll call a re-entrant corner or irregularity, where the house just pops out and juts out. I also see this one wall that we're looking at as all windows. I don't see much resistance strength of the walls in that slide. Another picture of it again, big overhang, but again, not much in the way of walls to help brace it against earthquakes. And another example, corner, where you see re-entry corners, different walls coming in at different places. And it was probably built in the 30s, perhaps the 40s. So it doesn't have quite the tying together elements that we as engineers would prefer. How does the loads go through the building? If we think just intuitively, you know that if you're going to have the weight of the building, you've got to have some strength in the roof, and the roof has to be supported on the walls. And then of course the walls are connected or at least bearing on the ground. In earthquake work, it's the same way, except it's a horizontal force. That force is the weight of the building being shaken by the ground. And as it's shaken, you get these forces. So in this photo or in this sketch, you see this end wall here, and this mass of the end wall is what I'm trying to show. And it's connected here at the roof line and transmits across the roof. And then this transmitting across the roof, it gets to this line and then is carried down to the ground. Now at each point, we need to connect adequately. We need to connect the roof to the wall, then this roof to this wall or this shear wall, and then the anchor bolts at the foundation, and then the load gets through the ground. That's the way an engineer would look at this. And here you see it again in this one here, forces of inertia act against the wall. And we're dealing with inertial forces. and then the forces push this way, and the wall holds it back this way. And all that's going on as the ground is shaking. As engineers, we look at it both directions, as the view on the right. So you see the force going in the east-west direction, I'll call it, and we have to anticipate, calculate the walls and the stresses. And then we design it in the north-south direction for the forces and in that direction. And those become numbers, and those numbers are based on the particular site that you're at. It may vary depending on the type of rock that your ground is, whether it be clay, sand, different densities of rock will affect the forces in your building. So it becomes a site-specific design in some ways. So let's look at these retrofit strategies then. So our options include enhancing the performance of existing elements. So if I have some walls, can I nail them up a little better and add some bolts to improve them? Or could I add an element? And we'll look at some slides later in Maria's presentation again about adding elements to strengthen buildings. And I emphasize adding elements because sometimes if we can integrate our seismic retrofit with other alterations, or perhaps are making inside the house, we can get the elements, both the new work to give us some seismic improvements. And then improve connections between elements and maybe look at weak links. And here's just some sketches of connections together. And what you see is that the roof sheathing is nailed to this blocking. The blocking's then nailed to this block. The plywood's nailed to this block. And then the plywood comes on down to the foundation. Now, I won't sing that leg bone's connected to the knee bone or anything like that. We'll just stick with, I won't quit my day job. Okay, what happened here? And here's a typical shear wall. When we talk about shear walls, we'll again look at the plywood that goes on it and the nailing of the plywood around the perimeter and at the joints. And then you see there's our new anchor bolts that installed and hold down anchors, because the wall, as the roof is pushing here, this wall wants to rotate and turn. So we have to hold it down here and here, depending on which direction the earthquake is coming. Not all walls need hold down anchors, but I point that out, and you'll see more of that a little later. The nailing is also important and depends on the load in the wall. The closer the nailing, the stronger the wall is able to resist the earthquake forces. So as engineers, we specify the thickness and type of plywood and the nails and the nail spacing. Okay.
All right. Do we have any questions so far from our folks in the audience? Haven't seen any coming on the Q&A, but feel free to type those in if you have any questions before we move on to the next section.
There was one question about a recording of it. Will the recording be available in night? I answered it, but just to verbalize to everybody, it is available. You can go to the CPF Facebook or YouTube page to find the recording pretty much immediately after the program. So we'll also email you a link after the conclusion of today's program with a link to the recording.
Great. Thank you, John.
Now we're going back to the quiz.
Yeah, I don't see any questions coming in, so I think we can move on to the next quiz.
Is that Maria?
Yes, I can share the next one.
Great.
And we also want to understand what you think is a construction type of your house before we go into some retrofit strategies. John, do we have good number of participation?
Yes, we have 17 responses now, so I'll end the poll.
Okay.
Should we share this?
Yes,
Yes.
please. Okay. It looks like 16 out of 17 is wood light frame and 1 is Adobe or stone masonry bearing wall. So this is great. We will cover all of these in the next few slides. So I'll describe a few retrofit techniques and show some examples of how those techniques were applied on certain projects. So as Mel mentioned with seismic retrofit, it is about the load path. And when we think of the load path, we start to capture the load at the roof level of a house and track it down throughout the walls of the house and bring it down to the foundation. So the first component of a retrofit mostly entails providing some type of diaphragm at the roof level. And this is done by adding roof sheathing in the form of new plywood over an existing house. And the photo you see on the left-hand side is new plywood sheathing that has been installed on top of an existing historic structure that had a gable roof configuration. And the image on the right shows, and this is a similar image Mel shared a few minutes ago, it shows what types of connections are used to attach a diaphragm of a house to the interior, exterior shear walls. It involves adding some blocking to receive nails that go through the plywood, adding some clips to attach blocking down to the top plate of the wall, and nails that attach plywood sheathing on a wall to top plate of the wall. In some instances, we also add, as you can see in section B, some ties that are either vertical or at an angle, and similar in section C, blocking can be provided at an angle, and clips that can be angled can also be provided to complete the load path from the plywood sheathing of the roof down to the plywood sheathing of the wall.
And then as the architect in the on the panel, we want to make sure that people are thinking holistically about these projects, and the installation of the diaphragm really typically requires that you remove and replace the roof. And it also provides good access to the attic. So in the photo on the right, we see a spray-in perlite insulation that was added above the ceiling level. And that's an excellent and cost-effective way of starting to control temperature within the historic home. And this also provides an opportunity to improve roofing and drainage systems. So the photograph on the left shows a new what they call valley, where the two gables meet. It's kind of the diagonal copper piece. New roofing. And it's also critical, and we'll talk about crawl spaces a little later, that we provide natural ventilation to attic spaces so they can not be too hot or too cold, and that gas or something from a fireplace doesn't get trapped within the space and lead to other problems.
Thanks, John.
Yep.
Another component of a retrofit and completing the load path from the roof to the foundation are collectors. And if you look at the illustration on the right-hand side, what I have highlighted in red is what we would consider a collector. And what a collector does is it attaches one part of a house to another part where the shear load needs to be transferred to a shear wall that we would like to act similarly to a shear wall that is located in another part of the house. And the detail across a collector typically looks like a strap that gets added between an existing wall. In this case, it was the existing exterior wall of the house you see on the right-hand side. And it gets received by pieces of blocking that you see here that get installed between the floor joists of the two-story part of the house. That way, if the two-story part of the house tries to move in, say, towards the left-hand side, it kind of will drag this smaller part of the house along with it. So these two pieces of the same house don't separate and move apart. And that's what a collector does. And what you see on the left-hand side in the photo is what a collector that has been installed looks like. This collector was installed under existing hardwood floor of the building over a diagonal sheathing. And the wall you see in the photo has been prepared to receive plywood sheathing. So it's a shear wall, a new plywood shear wall that's going in, and the collector is delivering the load at that floor to this shear wall as the shear wall continues down to the floor below. And the next part of retrofitting a house is related to shear walls. Now that the load is properly connected at the roof level, and we can utilize collectors to transfer the load between one part of a house to the other, the load then goes into a shear wall. And this picture you see is an illustration of what the various components of a shear wall are. The plywood sheathing engages all the studs of the wall together. And then at the foundation level, the load gets transferred down to the foundation using the base shear anchor bolts. And as the shear wall tends to rock and overturn, these are hold down anchors at each ends of the shear wall that keep the shear wall down. So this is an illustration of how a shear wall is put together in a sense. And the photo you see on the left-hand side is an example where sheathing, in this specific case, it was shoreboard sheathing that has been installed on an existing historic house on the inside face. And shear walls for a retrofit of an existing building can either be added on an existing wall that does not contain any plywood sheathing or any form of sheathing, or they can be installed as a new shear wall altogether, where a new partition wall or exterior wall gets built and receives plywood sheathing to act as a shear wall. So the photo on the left was an instance where an existing exterior wall was enhanced to also become a shear wall by adding shoreboard on the interior face of the wall. And the illustration on the right shows how shear walls can be located at various locations of a house, be it interior over existing partition walls or new partition walls, or along the exterior of a house.
Maria, it's John.
Sure.
I just wanted to chime in that often people are doing some small interior renovation with a project like this. And sometimes that provides an opportunity to either install a new wall or, put shear panels on top of an existing wall in addition to, moving around some rooms or maybe enhancing a kitchen or something like that.
Yes, absolutely. Thank you, John.
Mm-hmm.
And once the seismic load is in the shear walls, the next part is to deliver it down to the foundation. And that's where foundation anchors come into play. Foundation anchors can be installed in a few situations, as you can see in the illustration on the right. In section A is a case where a foundation anchor has been installed on a slab on grade type of foundation system. And in sections B, C, and D, it's where foundation anchors have been installed in, specifically in C and D, have been installed in a house with a raised foundation system where the anchors are installed into concrete stem walls. So the photo on the left shows what these anchor bolts look like in a shear wall. They go through the bottom plate that is connected to the concrete slab on grade in this case, and have washers, and then they're just bolts that extend down to the foundation. For types of houses that also have cripple walls under the first floor framing, we have a retrofit scheme to properly brace the cripple walls. And one way of bracing the cripple walls, as you can see in the illustration on the right, is by providing plywood sheathing on the interior face of the cripple walls. And as part of providing the plywood sheathing, we also add clips that connect the blocking under the first floor to the top plate of the cripple wall, as well as providing foundation anchors that connect the cripple walls down to the concrete foundation below. And what you see on the left-hand side in the project photo is where the cripple wall retrofit plywood sheathing had been installed on the interior face of the crawl space, and the foundation anchors have been installed under the cripple wall. And since we're looking at this photo from the exterior face, this means in this specific project, the exterior siding was removed for preservation purposes, and it gets reattached back on the outside face. So the outside face of the structure doesn't necessarily get altered because plywood has been added, because the plywood was added on the inside face.
Maria, could you actually go back a slide?
Sure.
So it's important to consider again ventilation of crawl spaces, and crawl spaces need to be ventilated for a lot of reasons, but one is that should water or moisture get into the crawl space, you want to make sure that it's able to dry out. And in the diagram on the right of this slide, you'll notice that vent holes are being drilled through the plywood that's on the interior face. So should moisture get into the wall itself, the wall has an opportunity to dry out. And then if you move to the next slide, in a similar fashion, you want to make sure that the crawl space has natural ventilation. Again, should there be a buildup of gas, or should it get damp underneath, you want to make sure that air can flow through. The building in the photographs is the same one, and it's in two different stages of a project. And you can see the approach that Maria was talking about in the right-hand portion of the upper photograph, where the plywood shear was added to the inside face of the cripple wall. And because there was a porch and the loads weren't so great, you'll see on the left-hand portion that under the porch we didn't have the plywood in this case. And then below, in addition to adding new electrical systems and service, you can see there's a white vent below the window, and that's to make sure that the crawl space below the house is adequately ventilated, and there's a detail showing that to the right of the slide. We also encourage folks to insulate the underside of the floor framing and sometimes to add a vapor barrier, depending on where you live, in order to, again, reduce your electric bills and reduce air infiltration into the home.
Thanks, John. David also mentioned this earlier in terms of resources available, and one of the resources available specifically for Cripple Wall bracing is through the California Earthquake Authority, and it's called a Brace and Bolt Grant that can be used for retrofitting Cripple Walls, and they have an illustration of what it all involves.
The Earthquake Brace and Bolt program will provide up to $3,000 for seismic retrofits of homes constructed before 1979 that have a raised first floor supported by short stud walls called cripple walls. Older homes supported on cripple walls typically lack sufficient earthquake bracing under the first floor. These houses with unbraced cripple walls are vulnerable in large nearby earthquakes. With strong earthquake shaking, unbraced cripple walls allow the house to move excessively and may topple off of the foundation. To determine if a house has a cripple wall, access the crawl space under the first floor. The crawl space is typically accessed from outside the house through an opening below the first floor. However, sometimes the access is through an opening in a closet floor inside the house. The qualifying cripple wall house has a wood first floor supported by short wood studs at the exterior and on beams and piers at the interior. The exterior cripple walls are supported on a continuous concrete or masonry foundation. To qualify for the brace and bolt program, this stud cripple wall may not exceed 4 feet in height. Earthquake brace and bolt projects must be completed using the California Existing Building Code, Appendix Chapter A3. The Chapter A3 retrofit requires the installation of new foundation anchors and cripple wall sheathing for bracing. To install foundation anchor bolts, new blocking is placed between two studs at the location of the new anchor. A hole is then drilled through the block and into the foundation. The hole is then cleaned thoroughly. To install an adhesive or epoxy anchor, the adhesive is inserted into the clean hole in accordance with the manufacturer's recommendations. A threaded rod is inserted into the fresh adhesive. A plate washer is installed and is secured with a nut. Expansion or wedge anchors may also be installed. Required anchor size and spacing is specified in Chapter A3. The retrofit also requires installation of new plywood or OSB sheathing on the inside of the cripple wall. The sheathing must be continuous from the mudsill to the top of the cripple wall. Sheathing size and length is specified in Chapter A3. The sheathing has vent holes and is nailed in accordance with the code. Finally, most CEBC Chapter A3 retrofits require installation of new framing clips at the top of the cripple wall. For houses with short cripple walls, there may not be enough room to drill a vertical hole into the foundation. Foundation plates approved by the building official can be installed between the mudsill and foundation in lieu of anchor bolts.
So this video, we chose it because it shows what the process of bracing an existing cripple wall entails. Another component of retrofit to address vulnerability is for houses that are located on a hillside. The reason that hillside foundations are critical for retrofitting is because when the seismic force is applied on a house, or as the house is experiencing ground motion, as you can see in the illustrations on the right-hand side, because the base of the house is not located at the same location, it tends to experience damage that gets amplified depending on how high the base of the house is. And in some instances, it may also result in what we call torsion or twisting of the house because of where the base of the house is at one end versus where it is located on at another end. The photo you see on the left-hand side is, apologies, is actually just a damage of in a house that is located over a hillside. As you can see, the house had slid to the right, and the steps you see in the photo along the grade line is a gap that has been created when the wood wall that was sitting on the concrete foundation had separated and had slid to the right. Now we're moving into a retrofit of vulnerable components of a house. And as this was mentioned earlier, one of the most vulnerabilities in wood-framed houses with chimney that is made out of brick is separation of the chimney from the house. So chimney retrofit, as you can see on the right-hand side, usually entails connection of the brick chimney above the roof line, connection of the brick chimney at the roof line, as well as connection of the brick chimney at the floor line if it is a multi-story house. And in plan, as you can see in the plan detail A2, the connection entails addition of a strap that wraps around the brick masonry and gets connected to the ceiling joists or the floor joists at the floor level. And the photo on the left shows a strap that has been installed at the ceiling level of a house. The chimney in this photo is located right here on the left-hand side. You can see the corner of the brick. But what the strap is doing is it's tying the chimney back to the ceiling joists, and the strap extends long enough along the ceiling to have enough connection so that the chimney doesn't peel off of the building. And now we go into retrofit of masonry buildings, and Mel will go over this.
Sorry, I think actually if we could do we have a couple questions related to the wood framing retrofits that might be good to address before we move on. The first was, what kind of clips attach directly to the roof ply when you're reinforcing the roof diaphragm?
Let me reshare that slide so I can explain it. So the clips that you see in this detail, we have one type of clip in section A, similar type of clip in B, and it looks like C is a unique one. So these clips, we refer to them as A35 or A34 or LTP clips. Some come flat. Those are the LTP clips. Some come pre-bent. Those are the A34 and A35 clips. And some come that can be bent to whatever angle you need, and those are variations of the LTP clips. But the types of clips are just variations of LTP and A34, A35 clips.
If I can just add a comment in here, these are literally off-the-shelf items is the key point. There's nothing exotic that we've been doing here for the most part. And the terminology that Maria used was for the Simpson company, but we're not promoting Simpson. There's other firms out there that make metal connectors. But they are, you can go to Lowe's or Home Depot or other similar, any place of building materials and find these kind of clips.
There is a follow-up to that. Do you use screws as the plywood is 5/8 inch thick?
Go ahead, Maria.
Yes, you can use screws. You can also use nails that are capable of going through 5/8 thick plywood. Both can give you similar performance for a diaphragm. In some
Great.
instances, and I'm sure Paige and Turnbull can add to this, if we have plaster that is sensitive, in those instances, we've used screws over nails.
Great, thank you. And then we have another question about whether drywall can act as a shear wall from someone who, for example, has a single wall house where they added studs and sheathing or just drywall inside of the studs to finish the walls of the single wall house.
Do you want to take this one, Mel?
I'll just, drywall misbehaved in past earthquakes. When I say misbehaved, it cracked a lot and had a lot of damage. And after the 71 earthquake, the capacities for drywall were reduced by 50% because of the damage observed. But it is still permitted in some zones or some regions, and may be permitted. I'd have to check the code. I'll just say there may be other places where it's permitted. But the experience with the drywall indicated we wanted to just put low loads in them. And you can do it. You just have to acknowledge that you're probably going to have more damage in an earthquake than if you have plywood.
I would agree. I'll just add, it's better than nothing, but we would certainly recommend plywood. And then you could cover that up with sheetrock if you wanted.
Great, thank you. All right, and then there was a question about, I guess I'm a little unclear. David, you had a message in chat, not David Koch, but David, an attendee, a follow-up question to the screw question about at reduced values. Can you clarify what your question is, please? Okay, I guess the question is that a screw into 5/8 inch thick has very little holding power, I guess, relative to nails. I guess it just depends on what all you're going into.
I would say he's not incorrect. That's one of the reasons that drywall just is not as effective as plywood.
And in the context of for a diaphragm, whether you're using nails and screws, when you're looking at the capacity of a diaphragm or the requirements of a diaphragm, if you're swapping it with screws, the penetration you would get from the length of nail that will be required for that capacity, you would have to get the same penetration from a screw. So you would use the same length screw as you would the same length nail. In that case, you get the same penetration into the wood and the holding capacity does not get reduced.
Thank you. All right. I think there's some other questions that I think are better saved till the end of the discussion. So let's move on to Mel's section on masonry retrofits.
What happened to my picture here? Hang on a second. Okay. Can you see my screen? No. Here we are. Okay, sorry for that delay. Let's take a quick look at a retrofit of masonry structures. And typically those would be brick buildings, unreinforced masonry, typically, adobe, and other types of structures such as stone and hollow clay tile. And the principles and the concepts still apply. You have to connect things together, and you have to make sure that they're adequate. So here on the right is a detail. We'll look at that in just a moment. But the principal failure mode of masonry walls is that the wall falls outward from the floor. It falls out this way. So our goal is to hold it back. And what you'll see in the retrofit of many commercial buildings is the steel plates on the outside of the building, perhaps spaced 4 feet apart. The plates are about 6 inches square, and the bolt goes through the wall and into the plate, and then connects to the floor itself, as shown by this construction here, which has a steel strap and an angle and stuff, and connecting everything together. And this would be the same concept for a stone building or even a hollow clay tile and adobe. We do them all like this. Typically, those bolts are epoxy adhesives, and notice that they don't go through the wall. By putting them, if you ran them straight through the wall, you grab about a handful of bricks that give you strength. If you run this at a diagonal at 22.5 degrees, I think you'll find 7 to 9 bolts, 7 to 9 bricks are connected together in this work. So you can draw a sketch there. Key point is that the bolt does not go through the wall. So visually, there's no impact on the historic fabric of the building. This one is where joists are parallel to the wall. Here's the joist. If we go to the next slide, here it is perpendicular to the wall. Same concept applies though, and so forth. Here's an Adobe house out in, I think, La Quinta or Indian Wells. It's an early home out there. And before our building codes really had provisions for Adobe. There are provisions in the building code at this point for Adobe, but not in the California building code. But if you want to build an Adobe in New Mexico, Arizona, or elsewhere, you're fine. Notice this is just typical of the wall. Here you'll see that this area actually was a deck and they built a room over it. But this part is Adobe and it's like a cantilever from the floor up. I'll show you another photo. And inside, the house had been vacant for a while. You can see the moisture got in here, probably from a lawn sprinkler. This is the living room. And obviously that's been fixed up now. In the second floor, we place these little steel posts, probably 3 by 3 or 2 by 2 steel connected to the floor. And that keeps this part from falling outward. Doesn't have to go all the way to the top, just enough to where you reduce the motion. And this was their boy's bedroom when the house was done. These were obviously or probably covered up, I don't recall now, and furred out with finished material. In the living room, what we do in Adobes and many other buildings is put a collar in or a bond beam. Just as your collar holds your head on, these bond beams tie the walls to the floor above. So here you see it's a steel angle iron bolted into the Adobe and then bolted up into the floor joists above. The bolts obviously don't go through. And then here it's kind of finished. The owner chose to paint this to pick up the theme of the beams itself. And this is a finished building and it's retrofitted. So that's that. Okay, whose turn is it? Anyone there? Is
It's
there any
my
life
turn,
out-
Mel.
Maria's gonna go through.
Any
Yes.
life out there?
So we will revisit the quizzes, the quiz questions from earlier now that we've showed you some retrofit schemes. John, I don't think we need to run the answers again. I could just go over the answers without having to do the poll again. So this photo, I think everyone got it. It's more or less straightforward. The retrofit that would have prevented this type of failure and address of vulnerability would have been addition of foundation anchors. And it looks like everyone had it right. And as you can see in this photo, specifically along the top of the concrete stem wall, it looks like there were no bolts at all that could have prevented this house from sliding off.
May I make a comment here?
Sure.
Okay, if you recall back to the slides earlier that Maria showed, the anchor bolt, when installed, the new anchor bolt had a 3-inch or 2.5-inch washer. And we found that in the 1994 earthquake, that just the bolt without the washer actually ripped that plate, the wooden plate at the base. And that's when the code was amended to require that. So that's an important element, the washer is.
Thank you, Mom. The next one was this photo, and 13 out of 14 had it right. This photo is a collapsed chimney from an earthquake. So as you can see, the base of the chimney, parts of it are still attached to the roof of the house, but the remainder of the chimney had just toppled over. Luckily, is still on the roof and hasn't fallen through. But chimney bracing would be what is required to prevent this chimney collapse. This one had 75% of the responders as correct. This one, a shear wall retrofit would have prevented this failure. This one is not as straightforward, even though the arrows are pointing to the areas of damage. What has happened is the shear walls, or lack thereof, maybe they exist at the piers or at either sides of the garage opening, are not sufficient enough to properly transfer the force that's at the roof level of the garage down to the foundation level due to this large opening. So the type of retrofit that would be required in this case is supplementing or providing new sheathing along these two piers of the garage opening. That way they're stiff enough and they can resist large amount of deformation from happening.
Just one more comment, if I may. There's a number of proprietary products out there to work at those two narrow piers that you just described. And there's several manufacturers here in California that can provide that as an option to the plywood. Depends on your conditions.
Correct. And they come at various lengths. So they're simpler to install depending on the length available at either sides of the garage openings. The last one was 16 out of 17 said Cripple Wall sheathing, which is correct, and 1 out of 17 said foundation anchor bolts, which is also correct because you would install foundation anchor bolts as part of the Cripple Wall sheathing. This photo and this failure also is that of a hillside. So as part of the hillside retrofit for this specific house, cripple wall sheathing and bracing and foundation anchorable addition will all be included as part of the retrofit. So this one was not as straightforward, and the split between the answers was more or less expected. David, Mel, anything else you would like to add for this?
Just say there was debate in the project team what the risks were with this, so it wasn't quite so clear cut.
And this photo also shows an insulation of the first floor framing that can be added when you get access to do work on the cripple wall through the crawl space. Do we have any more questions, Sarah?
I see one from David again, related to one of the.
Oh, sorry, I was just muted. Sorry about that. Yes, we have one related to this section. I think there's another one that we'll save for closer to the end of the presentation, but a question related to the picture with the failure, the shear failure around the soft story opening on the garage, saying that it looked like the aspect ratio wouldn't work for shear walls. And I think this probably gets into another conversation our team was having earlier today about other options you would have for an opening of this size. So I don't know if we maybe want to touch on that now.
Okay, so I would assume based on David's question that I can give a more technical answer to this and not worry about it being too complicated. So that is correct. The aspect ratio of majority of garage openings do not meet minimum aspect ratio required for plywood shear walls. That's where the proprietary products that Mel mentioned come into play, that are specific for the pier, short pier lengths. 18 inches, 24 inches can be accommodated by those types of proprietary shear walls. And another scheme that the project team discussed early on was also moment frames, which I understand is not a scheme that we had mentioned earlier, since moment frames are not typically used in single family dwellings, but garage openings are sometimes locations where moment frames can also be an option for retrofit.
All right, and then we have another question just asking about post and beam foundations and how you, I guess, how you would deal with that if you have a post and beam framed structure.
You want me to dive in?
Yeah, go for it.
Okay.
I don't have a photo.
Posts and beams are not, and I'm assuming what you're talking about is a house on stilts, where there's it's elevated, there's air underneath the house.
Oh.
There might be some diagonal bracing between the posts, and they come down and typically would sit on a very small pier. And if it's an older house, that very small little concrete pier may not be very well embedded into the soil. It might not be very deep. There's really two ways you can do it that I can think of. Number one would be to go in and actually excavate. It depends on the geotechnical requirements also, but to excavate a trench around that interconnects each one of the bases of those posts and create a grade beam, or it would become like a foundation, a strip footing for the house, and it would be, you would end up having it almost a grid of foundation beams or grade beams. So that's one way to do it, and probably easier and less expensive than the other way to do it, and that would be to go in and drill caissons to pick up the bottom of those posts and attach to those. It's not an easy thing to do. And there's lots of different techniques we could use, but those are the basic concepts for how we would tackle those. But I would, especially if it's on a hillside, you're going to want to talk to a geotechnical engineer about it also. Hope that helps.
Thank you, David.
Looks like we have some additional input from our audience about an option potentially for continuous sheathing under conventional bracing for between the piers. And I'm not sure if this is talking about the post and beam foundations or back to the situation with the garage. But then there's also a question about whether if shear by rotation is still allowed.
Shear by rotation?
I'm not sure what shear by rotation,
means.
what he's referring to.
In that section of the California existing building code, there's this in the foundation, it talked about rotation, and that's where we permit the building to quote rotate, and then the load goes into the opposite walls. And it said with permission of the building official, and there may have been some other conditions in there. So it's not an easy question, just say yes, no.
And I assume, Mel, we're talking about the existing building code, not the historical building code.
Correct.
Yeah, the historical building code would not, you wouldn't have to necessarily address that. You're not required to address that. But the existing building code, just as Mel said, it's telling you that you need to address it or talk to the building official about it.
Thank you.
Where are we going?
Next is phasing
Okay,
priorities.
let me get back on track here. So I have to share again.
You have to share again. We're on slide 68.
Yeah. Okay, sorry. Does a lot of thinking here. Let's talk about phasing. And I think this is an interesting workshop, these couple meetings, because too often, from my point of view, we get focused on one thing like foundation and anchor bolts and cripple studs and don't think about the other aspects of this. So I think it's been a good session, at least for me, to stand back and look at the whole building and select the priorities that may apply. I put two ranking measures on the side here for wood frame and then masonry structures, and I'll get to those in a moment. But what are the priorities? If I have, obviously, all of us have a limited amount of money and we want to make it get the most bang for the buck. And I'm going to tell a story. David said it before, but for cripple wall bracing, which I put as number one, in my opinion, I saw these houses in Watsonville after the Loma Prieta earthquake, and they all fell off their foundation with cripple wall failure like dominoes. And I said, we could have fixed that for, this is a long time ago, $2,500 and brace those foundations. Instead, they got $30,000 to $50,000 of house moving expense to jack up the house, put it on, and so forth. So you get a lot of bang for your buck with cripple wall bracing. And that's why the California Earthquake Authority pushes that too. Obviously, anchor bolts into the foundation are important. And then open fronts, which Maria showed very well what goes on in the potential for hazards at an open front. Porches are an important thing. In older homes, the porches are not well connected to the building, often just with wood ledger and some nails. And a not uncommon event in earthquakes is the porches falling off. We showed a couple of those in workshop number 3. And the porches falling off, so it may not sound like much unless it happens at both your front door and back door, and suddenly you cannot open the door to get out. So think about that. and obviously other falling hazards, ornamentation, and so forth. Shear wall additions, you notice I put lower, but it's still there. And then obviously the chimney bracing. Now, in masonry structures, parapets are critical. They stick up above the roof, like I showed you in that Adobe, and they fall, they rock and fall first thing in an earthquake. And we've seen that in earthquake photos all over the time, all over the place. So parapet and gable end bracing also. Falling hazards. And then the most important thing after that is obviously out of plane anchors so that the wall does not fall out. If you want to get into greater detail, we can look at diaphragms and how strong they are, how weak they are. Wall stability. Walls, if they're too tall and thin, can be a hazard. Churches and other buildings like that, movie theaters and so forth, sometimes that happens. In-plane shear is another issue. Not really a big issue in our single family dwelling. So I think we can get the items 1, 2, and 3, we're in pretty good shape. So then the second point is there home improvements that I can integrate into seismic retrofit? We did a series of books for FEMA on incremental integrated seismic retrofit, which are available free on FEMA's website. The key point is if you're modernizing a kitchen or revising a bedroom, sometimes changing a wall or openings in a wall, you may want to take a look at improving the walls that way. And lastly, you see there's a lot of engineering in here. And I think you need to find someone, an engineer or an architect, who's qualified and experienced in this. There's many design build contractors, particularly for the cripple wall bracing and anchors that are out there too, that know what they're doing. So in phasing, consider the full range from do nothing, which is our collapse on the left, to safety and reoccupancy. Functional recovery we won't go into, but you want to do enough so that you can shelter in place after the big one. You know, that your house is there, that you can be there and stay rather than sleeping in a tent in the park or wherever we've seen it in past earthquakes. And there still may be damage, but it may not be to your detriment to your safety, I guess is what I'm saying. Also keep in mind that we really haven't had the big one. Whether we will or not is, well, we will someday, but in our lifetime. So, but in that time, there's going to be many 5s or 6s, as like the Northridge earthquake or Loma Prieta. So this investment that we're saying here, and that David described as almost self-insurance, is wise to consider. Again, if you're going to do something incremental, develop priorities, because most of us cannot do this all at once. Get a sense of the cost for each mitigation task, and like I say, integrate with other products, and then consider the financial vehicles, and they're going to discuss that more. We saw a little of the brace and bolts. There may be more in the next workshop 5. So
we are going to briefly identify a couple of financial incentives that exist for historic houses and sometimes existing houses. So these are fairly specific to California, but there are similar types of incentives in different states, and they do vary. So the first one is just a grant program. I like grant programs because they basically give you some cash. So the California Earthquake Authority's Brace and Bolt Grant Program, and they offer a few $1,000s for basically bracing, and bolting your house to the foundation and bracing things like cripple walls. And it's important to note that in 2 weeks here the program will open for this year. A incentive that's unique to California is the Mills Act property tax abatement. So in a Mills Act, you enter into a contract with your local municipality, and the rules do vary somewhat depending on where you live and what that municipality is. But effectively, they will reassess your property, and there's 3 different methods, and we'll go into it in more detail in the 5th workshop. But you can get a property tax savings in exchange for, I would say, maintenance and repair of historic homes, and there tends to be an emphasis on prevention of, I would say, catastrophic events like collapse and earthquake or fire. Another one is the California Capital Access Program. So they offer low interest loans for seismic safety improvements to your house. Soon there is a state historic rehabilitation tax credit coming to California. Many states, I think 30 states have this in place. The measure, the legislation's been approved, and they're just working through how they're going to administer the program. It will be a competitive program, but unlike the federal tax credits, single-family homes will be eligible for this program. And there are also preservation easements. It's not listed on here, but that's actually another method for getting some money to repair, restore, and secure your home. Next slide. Oh, sorry, Mel. Next slide, Mel. There we go. Oh, we've got a couple more to go. I can share.
Yeah, do that, because mine just said there were no more.
Oh, okay. Yeah, there's a few more. I gotta get my show going too here. Oops, you don't want to see it from the beginning.
Getting seasick.
Yeah, I'm sorry. Current slide. So we've come to the end of our presentation. So I'll give a very brief summary, and we will move into questions. So a key point is every improvement helps, and you know, it is very feasible to phase this out and do small projects over time to make your house, to improve your house for seismic safety, but also other things as well. You know, in opening up homes in order to do some of these repairs, you can tackle things like electrical wiring. Insulation is a favorite of mine, waterproofing, and other in repair and restoration of some historic fabric as well. So it is important to kind of think strategically. Evaluation of the home is, or the building is important to understand seismic vulnerabilities, weak spots, places that may not be connected, or places that may not be adequate to resist the forces of an earthquake. So, you know, taking the time to go through and identify those weaknesses and then target retrofit strategies. The next point is a critical point, and there are lots and lots of professionals out there who are qualified to help you work through this process. And I always like to say it takes a team to do these things. So finding people you trust and would like to work with is important. There's a whole slew of different retrofit techniques out there, and we went through some of the more common examples, although I don't think Adobe is all that common. And then there is a strategy that we've provided to kind of thinking about, the most important thing to retrofit down through. And there's a note in there to think about non-structural items like your, bracing your water heater. Fire is a major cause of damage and associated with earthquakes as well when a gas line breaks or a water heater falls over. And then bookcases toppling, can cause serious harm and make things, make your house more difficult to access in a lot of ways. So with that, I wanted to note that our next workshop will talk more about repair and rehabilitation and the correct way to deal with these retrofit projects and then put everything back so your historic home continues to look great. And that is Tuesday, November 8th. And our last workshop will be kind of the nuts and bolts of retrofits. And we'll be talking, in addition to a few structural items, also taking a look at weatherizing your home, improving thermal performance, and how you may integrate systems like we talked about, like electrical and heating, ventilating, and air conditioning into these projects. And with that, I have a set of resources that is available, and there's also a handout that comes with this that CPF will send out. And with that, we will go to questions.
All right, thank you, John. So the first question we have that came in a while ago, and I appreciate your patience, Bradford, as we got to this, but we have a question asking us to discuss in further detail the process and method for creating a cost comparison between retrofitting versus the seismic damage. And I think we touched upon this when we were talking about earthquake insurance, but I wonder if we can give a little bit more background on how you would do that, whom you might engage to help you with that process, et cetera. Don't all jump at once.
Well, that's a toughie. David may have something. I just say, for these smaller projects, I would often talk to a contractor that does remodeling work and so forth. That and you want to make sure it's a competent contractor. But and then these people that do the anchor bolts and cripple studs are also very knowledgeable on the costs. David, you have anything to add there?
Yeah, I would. I was thinking about that probably you would, and I would agree with you, Mel. You need, maybe what you could do is pick the brain of the engineer and go, okay, where are the deficiencies in the house? What kind of damage can I expect? What level of damage can I expect for each one of those deficiencies? And then turn to the contractor and go, okay, if you think we're going to have this level of damage, how much would you think it's going to cost to repair it? And so at least it's not scientific. And it's, there's not a lot of science to wood frame single story buildings or smaller single family homes. But at least that would give you a sense of, okay, am I looking at a $20,000 repair, or am I looking at a $250,000 repair? And then get an estimate for addressing those deficiencies, like we said. And you could even do them side by side. You could go, okay, if we do the Cripple Wall, like I said before, for $5,000, but it's going to cost $50,000 to repair it, that's pretty obvious. If we're going to do the chimney, and that's a $10,000, or it wouldn't be that much, but let's just say $10,000 retrofit versus $100,000 if the thing falls through the roof, and there's another one. So you can work your way through those costs and those benefits that way. The only piece that's missing there is, what is the probability that your house is going to be shaken to that level? I mean, you can roll the dice, like Mel said, and it's like, hey, it's going to happen 100 years from now, and I don't have to worry about it. Or it could happen tomorrow. And it's all very, very much a probabilistic kind of question.
Thank you.
I agree with that, David. I think some of the things that people don't think about cost-wise, and when you're thinking about repair, and this is kind of tricky when you're looking at any type of major retrofit or repair in any kind of building, really, there's all these buried costs. So, you know, if your house is red tagged, you can't live there, so you have to live somewhere else. So there's a cost associated with renting a property, or, you know, even living in a tent. And it's that type of cost that creates an even bigger delta. Like, you don't know what the repair costs are, but also you don't know, you know, how long it might take you to occupy the home, you know, how long the design and permitting process. So all these things start to build up. So,
Right.
you know, the damage repair can get really expensive really quickly.
Right. I might want to, I mentioned, we were talking about this a little earlier, the panel, that with Hurricane Ian in Florida, there's been several articles that have pointed out that the newer construction that was designed to the newer building codes actually performed much, much better than the older construction that was designed to the older building codes. And in fact, there's even a little town, a community, that they designed it specifically for resisting hurricanes. They lowered the streets so that the water would drain down through the streets and not go up underneath the houses. They had solar backup so they wouldn't lose electricity. They built the houses very stout per the new building code. So there are ways you can, we will never say earthquake proof, and nobody can ever say hurricane proof, but there are definitely, as we were saying before, every improvement helps. Everything you do is going to make your house a little bit more resistant to earthquake shaking.
We don't have any other questions in our Q&A yet. So if anyone wants to add some, please do.
There is a question in the chat. We're kind of mixing up now.
Yeah, yeah. And I did just note that, but I can say as well, the question was in the chat whether if you have an unreinforced masonry chimney that would be damaged in an earthquake and would have to come down, why would you not take it down beforehand rather than just, you know, strap it or do the reinforcing? Right. And it does depend a little bit on, well, it depends on a lot of factors. If you attended our last workshop, one of them is whether you need a chimney. So if you are actually using your chimney, then you probably wouldn't want to take it down because you would need that for the exhaust of whatever it is that you're burning. But the other thing is that a chimney is typically a character defining feature of an historic property. So if you do have a house that's in an historic district or is a listed historic resource or something like that, then removing that chimney would be an adverse impact to the overall integrity of that resource. And that would be a concern in, you know, whatever governing bodies are controlling what work you can do on the exterior of your house. So that would be the other reason you probably wouldn't want to just take it down and would want to find a way to reinforce it.
I think when we talk about historic buildings, you know, we take an approach of starting with kind of the least aggressive thing to do and then working through to the most aggressive. So the first thing you want to do is, you know, and this was covered in the first two workshops, is identify whether your chimney is a character defining feature. And then if it is, you know, the first priority, the first thing is to really preserve and maintain it. So take care of it, you know, keep the mortar in good shape, make sure the flue isn't cracked, and make sure, you know, the flashings are good so water is not getting in around the roof. And then if there are issues with it, to repair it. And with that, we frequently will say to enhance or upgrade. So that would be the strapping, that would be, potentially adding some bracing, but keeping the original fabric in place. And then if that's really not feasible for whatever reason, it may be condition, it may be cost, then really thinking how do I reconstruct the chimney in a fashion where it has the same kind of visual characteristics. So the construction may be different, but the visual characteristics are the same as the original. And then really only as kind of a last resort would you think about just taking it down and moving it down.
Right. And in my experience, that's typically when you have an immediate hazard that you would move to doing that. If it's in such bad disrepair that it's, possibly going to fall even just in a high wind, you're not even worried about, just an earthquake at that point then. But yeah, you could consider it in that case. But for the most part, yeah, you would want to do all the steps that John mentioned first.
Yeah. And we recommend that as part of that evaluation, right?
Exactly. Now we have a question from Alan asking, are there any companies that will do theoretical modeling of your home to evaluate what damage you might expect in an earthquake?
Go, Mel.
I'll just say that the dwelling or the wood frame buildings are such a complex interaction of different materials. So when we say the plywood, but the reality is there's other materials that are bracing the building too, either a lead and brace or drywall or early plaster with the wood last plaster. I think it's almost impossible, but there is one FEMA. It's really for apartment buildings, soft story apartments. I can't remember the number, but it integrates or tries to integrate all the materials into the analysis so that you use everything when you're trying to analyze the building, everything that's built in. And I just don't remember the number.
I don't remember either.
Yeah, but you can look it up on the FEMA website and you'll see soft story apartment buildings or soft story wood frame buildings. And you may find that of interest, and that may be a modeling technique that can be used to get a sense of what happens.
I would say typically though, Mel, at least for us, we would walk into a single family house, which is generally not going to be a really large structure. And we can do an evaluation, actually do calculations. It's not just pointing and fingers and saying that's going to break and that's going to break. We can actually do a mathematical calculation about to make a judgment about how we think it's going to perform. And so it is possible, I would say, and maybe this is after 41 years of experience and Mel plus that, I wouldn't guarantee anything, but we can have a very good conclusion that we can form recommendations based on that evaluation. It's not like somebody can just build a computer model of a house and push a button and say, there's all your answers. So I don't know if that's what you're looking for. That really, if there was somebody that had a model that did that, I wouldn't trust it.
That's true. I got the chat is up to 15 here, Sarah.
Yeah. All right. Haven't seen any other questions come in. I guess we can leave it a moment and just see if anything else comes.
One thing about chimneys is that the flue dimensions in the older chimneys are often just, the chimneys are like one brick thick, and then it's the flue, and that won't, if you want to rebuild it, that won't work. So you have to carefully consider the impact of the work. Most of our chimneys that we've rebuilt have been with steel studs and a brick veneer rather than and trying to get close to the original dimensions. It's not
Right.
quite as easy as rebuilding.
Mhm.
And sometimes we would choose to cut them off at the attic level,
Yeah.
Right.
leave everything below, and then go from the attic level up with the new metal stud framing and the metal flue.
Chimneys are
right.
interesting. I've seen lots
Yeah.
lots of different solutions.
Mhm.
Oh,
Some
yeah.
some very clever, some pretty ugly.
All right. I don't see any additional questions, so I think maybe John Haber, if you want to hop on and say a farewell, or if anyone else wants to have any last words.
I wanted to give a plug to CPF. I think they're going to be having a workshop on the soon-to-be state historic preservation tax credit, as I recall. So you can keep your eyes out for that.
Fingers crossed. Yeah, it was fascinating. I learned a lot, and I really appreciate everyone's time. We all appreciate everyone's time today. So thank you all. And just as a reminder, you'll find the recording on our YouTube channel, on Facebook. We'll share it by email with you. I also posted it in the chat. And in the chat is the link to an evaluation. So let us know how we did. Just a reminder on our end, we have our Design Awards programs this year, so you can learn about a number of fascinating projects, all of which are among the state's best historic preservation projects. So you can check out our website for that for the whole month of October. And then we'll see you on November 8th otherwise. And thank you all, and we'll see you then.
Thank you.
Good night,
Thanks,
everyone.
everyone.
Good night.